Hello and welcome to lecture 19 of Math 2R03. In today's lecture, we're going to look at section 5.c of the textbook. This is near the end of chapter 5. And in particular, what we're going to do is we're going to introduce eigenspaces and diagonal matrices. So when you're looking at this particular section, you want to think back to Math 1B03 where you learned about the diagonalization of a matrix. And that's kind of the main theme for today's lecture. So just to kind of quick recap and to kind of give some just kind of motivation for today's lecture. Remember in the last lecture, we showed that if we have a finite dimensional vector space over the complex numbers, you can find a basis of your vector space such that when you make the matrix MT, right, the matrix associated to that linear map, you can actually make it to be upper triangular for any linear map or operator inside of the set of all operators. So, that's a pretty good result. But the question is, and mathematicians are always interested in this, is can we do better? Okay, and what would better mean? Okay, so i.e., what we want to do is minimize the number of zeros. So i.e., can this matrix MT have fewer zeros? Okay, so an upper triangular matrix already has lots of zeros in the bottom left-hand corner. Can we make our matrix so that this matrix has even less zeros? And that's what we're going to be looking at in today's lecture. Okay, so the question is, what kind of matrix are we aiming for? Well, probably the best that we might hope for is an example of a diagonal matrix, which is something you saw in Math 1B03. So a diagonal matrix is just a square matrix where all the entries are zero, except possibly on the diagonal. Except possibly on the diagonal. And it's very easy to crank out examples of a diagonal matrix. So let me just give you one. So this would be an example of a diagonal matrix where all the entries off of the diagonal are zero. So I have zeros in the top right corner and the bottom left corner. And then I have some entries on the diagonal, and they can be zero or not zero. Okay, so that's kind of would be ideal to answer this question. Could we make this matrix a diagonal matrix? Well, to kind of tackle this problem, what we need to do is introduce kind of the correct subspaces of our vector space. So whenever you have a linear operator, you actually get lots of subspaces corresponding to that. And now what we want to look at is actually subspaces corresponding to eigenvalues. So first of all, in the definition here, we have a linear operator and we have a number. So we're not even putting any restriction on this number lambda here. And the eigenspace of the linear operator corresponding to this number is the subspace given by, and here I'll use the following notation. So the subspace corresponding to the linear operator and this number lambda is the set of all vectors v such that if I look at the operator t minus lambda I v equaling to 0. So I'm looking at making an operator from t and the number lambda, and I'm looking for all the things killed by this operator. So another way of thinking about it is what is the null space of this operator. Now, obviously, the 0 vector is always inside of here, but because it's a null space. But the question is, what else could be in there? And the point is that lambda is now going to be an eigenvalue if the corresponding eigenspace is strictly bigger than the 0 subspace. Okay, so the definition works for any number, and for most numbers lambda, this will actually just be 0. Okay, it will only be the 0 subspace. But you pick up an eigenvalue precisely when you get something bigger, strictly bigger than the 0 vector. Okay, and the other thing that we get here is that if lambda is an eigenvalue of t, then when you restrict the operator to the subspace here, it's the same thing as just multiplying by the number lambda. Okay, so let me just write that out. And you may be able to hear "Oh Canada" in French in the background. So T restricted to E, the subspace E lambda T, or the eigenspace corresponding to lambda, is the same as multiplying by lambda. Okay, so that's kind of important about these eigen values and eigenspaces. And the nice thing here, and we'll prove this in the next part, is that in some ways eigenspaces of distinct eigenvalues are disjoint. Okay, and so let's make this a bit more precise. Suppose V is a finite dimensional vector space, and T is some linear operator with distinct eigenvalues lambda 1 through lambda m. Then if you look at each of these eigenspaces, it's going to be a direct sum. And the dimension of this eigenspace plus the dimension of the second eigenspace plus the dimension of all the way up to the dimension of the last eigenspace, it's going to be less than or equal to the dimension of V. So when we come back, we're going to prove this, and we'll look at some more examples of eigenspaces and try to tie it back to Math 1B03.